Hello, my name is Rishi Puri, and I will be presenting joint work done with Professor AGNOSTIC and Rahul Puri focusing on Fewshot learning for point cloud data using ModelAgnostic Meta Learning. The ability of deep neural networks to extract complex statistics and learn high-level features from vast datasets is proven. Yet, current deep learning approaches suffer from poor sample efficiency in stark contrast to human perception. Humans are often able to adapt to recognizing novel images in just a few examples. This is the inspiration and goal of Fewshot learning for 3D point cloud classification. On the right, we see examples of point clouds classified by our system. Supervised 3D deep learning classification methods require large amounts of data to train. It is a very difficult task to ensure the trained model generalizes to a held-out test set. Even once this generalization has been achieved, it requires similar amounts of data to retrain or adapt these models to new classes. This is in stark contrast to human vision, which is able to recognize new classes of 3D objects given just one or two examples. Most humans possess this ability by their early childhood years. Meta-learning is commonly described as learning to learn or learning to be adaptable. Meta-learning aims to mimic human-like learning abilities. An intelligent human will progressively become better and better at learning, honing techniques to learn new concepts and skills faster and more accurately. A meta-learner learns tasks which consist of adapting to a certain problem. Similar to a human, a meta-learner learns to learn new tasks better and more accurately with each new task it faces. N/K shot classification is a subfield of meta-learning which aims to solve N/K shot tasks. In an N/K shot classification task, a model is given a support set and a query set, each sharing the same N classes with K unique instances for each class in each set. The algorithm must adapt to the support set and is then tested on the query set. We also refer to this as Fewshot classification. In the picture, we see an example of a 2x2 shot classification task with cats and dogs where we get 3 out of 4 correct on the query set. In meta testing, we train on a support set and test on a query set. We choose to use the ModelAgnostic Meta Learning algorithm, or MAML for short, to solve Fewshot classification as it is agnostic to model choice, allowing us to use complex, state-of-the-art point cloud processing architectures such as PointNet. MAML is model agnostic since it uses gradient steps to adapt itself, rather than needing architectural modifications to adapt as in many other meta-learning methods. In this paper, we extend the MAML algorithm to point cloud data using a PointNet architecture. We construct N/K shot classification tasks from the ModelNet 40 point cloud dataset to show that this method performs classification as well as supervised deep learning methods with the added benefit of being able to adapt after a single gradient step on a single N/K task. These are competing approaches to Fewshot learning. The Siamese network applies a feature extractor to two inputs and produces two feature vectors to be fed to a discriminator trained to output the probability that the two inputs belong to the same classes. The cited extension work uses a PointNet-like architecture to extract features from the point clouds. The matching networks framework essentially describes the output for a new class as a linear combination of the labels in the support set scaled by attention. Both of these approaches are confined to specific architectures and are therefore less versatile than our MAML approach. Here we visualize an overall picture of MAML. We start at the left with the meta-learner's parameters theta. We copy these over to initialize a fast model which is passed the meta batch of tasks. Each task is passed to the fast model. For each task in the meta batch, we calculate the loss the fast model incurs and compute the gradient of said loss to create an adapted model for each task. We then apply the task-adapted models to each task. We take the sum of these losses and then take the gradient with respect to the original meta-learner's parameters, theta. This second-order gradient is used to update the meta-learner's parameters, completing our loop. The MAML algorithm for Fewshot learning is shown in the algorithm here. Unlike most deep learning algorithms, MAML does not learn on batches of samples, rather on batches of tasks, also known as meta-batches. For each task in a meta batch, we first initialize a new fast model using the weights of the base meta-learner. We then compute the gradient and hence a parameter update from samples drawn from the task and update the weights of the fast model, i.e. perform typical mini-batch stochastic gradient descent to update the weights of the fast model. This is shown in step 7 of the algorithm with parameter alpha as the hyperparameter. After the parameter update, we sample some more unseen samples from the same task and calculate the loss on the task of the updated weights of the fast model of the meta learner. This is shown in step 8 of the algorithm. This process is repeated over a number of tasks as shown in the do loop in the algorithm, starting from step 4 and ending in step 9. The final step, i.e. step 10 in the algorithm, is to update the weights of the meta learner by taking the gradient of the sum of losses from the post-update weights from different tasks. This is the gradient of a gradient and hence is a second order update. In this step, beta is the learning rate hyperparameter of the meta learner and P of t is the distribution of tasks. This is a key step as it means we are optimizing for the performance of the base meta model after only a gradient step, incorporating task-specific loss functions and data activations into the meta parameters. The result of this is that the meta learner can be adapted by gradient descent on datasets as small as a single example per class without overfitting. PointNet is a novel system for extracting both local and global features from point cloud data. In our work, we modify the classification network in PointNet to take 2500 XYZ points as input. We choose 2500 due to the computational constraints. We follow prior work and apply input and feature transformations, and then aggregate point features by max pooling. The input and feature transformations utilize a T-net, which learns an affine transformation matrix. The output of the classification network is an n-way classification score as in n by k shot. The segmentation network is an extension to the classification net. It concatenates global and local features and outputs per point scores. We are only using the classification portion of the network in this work, but it would be a simple adjustment to extend our implementation of MAML to tackle segmentation using the same model or object detection using a similar model. PointNet functions within MAML since it can be trained through backpropagation. For preprocessing, any object with less than 2500 XYZ points is padded with zeros to become 2500 by 3. For objects with more than 2500 points, we subsample 2500 points of the total uniformly at random. Our MAML system uses the native PyTorch AutoGrad using CUDA 10.0 with an NVIDIA 2060 Super GPU for acceleration of training. Our architecture uses PointNet in PyTorch with a classification output layer of n neurons and a softmax cross-entropy loss and a argmax decision rule. We use PyTorch's implementation of Atom for optimization of the meta parameters. For the meta parameters, we use the learning rate of 4 times 10 to the negative 4 for n equals 3 and 5 times 10 to the negative 5 for n equals 5. For the task-specific adaptation of meta parameters, we use learning rate of 0.4. We use the Princeton ModelNet 40 dataset for our experiments. We ran n by k shot MAML on the preprocessed data for n equals 3, 5 and k equals 1, 2, 3, 5, and 7. To do so, we create a meta train and meta validation set using 24 classes for meta training and 8 classes for meta validation, saving the last 8 classes for a meta testing phase. This corresponds to 7400 for meta training, 2460 for meta validation, and 2460 instances for meta testing. We perform algorithm 1, evaluating the trained meta model on our meta validation set. In order to obtain metrics comparable to the test set accuracy of PointNet on ModelNet 40, we perform a meta test by partitioning our test set into disjoint tasks. The meta parameters theta are then adapted to support sets of these tasks and evaluated on the query sets. Each query set contains the same classes as its matching support set with different and unique instances. These classes are drawn by partitioning the 8 classes of 2460 instances into unique n by k tasks consisting of a support and query set. The average Fewshot classification on the query sets is then reported. This produces an accuracy percentage that can be compared fairly to the classification test set accuracy reported in the original PointNet paper. This test is fair as we hold out 20% of the data classes for testing. We use half of this, or 10% of the data instances, as a support test set for adaptation. We then evaluate accuracy on the other half, query test sets, which contain 10% of the data instances. This leaves us with an evaluation of classification accuracy on a held out 10% of ModelNet 40 classes. This closely follows the testing procedure in the original PointNet paper. K equals 3 achieves the best performance for both n equals 3 and n equals 5, with the best performance at n equals 3 and k equals 3. As seen in the table, n equals 3 performs better than n equals 5 in terms of meta validation accuracy and meta test accuracy. This may be partially attributed to the fact that n equals 3 begins training with about 33.3% meta-validation accuracy, while n equals 5 begins with about 20%. These baselines correspond to the result a random guess would achieve. The highest meta-test results for 3x3 shot and 3x5 shot and 5x3 shot learning slightly outperform the test scores published in the original PointNet paper using supervised learning tested on 40 classes. Although the comparison is not exact, it is still principled, as both tests involve classifying every unique instance in the test set. The main difference being that our MAML can easily be adapted to 3 new classes of point cloud at a time with as little as 1 new example per class for our 3x1 shot PointNet. In contrast, the traditional PointNet would need to be completely retrained from scratch, taking hours or days to learn just one extra class. We also report meta-test accuracy on 6 classes for Siamese networks, which we note to be lower than the supervised results and most results from MAML. The comparison against Siamese networks is more exact, as both are meta-learning methods. We now demonstrate the generalization capability of our trained meta model to a new 3x3 shot classification task. We choose the 3x3 shot meta learner since it performed the best. The data is drawn from 3 randomly chosen classes of ShapeNet models. ShapeNet is a dataset with 3D point clouds of everyday objects similar to ModelNet 40. For each class, we choose 2 pairs of 3 random instances which we pre-process to have 2500 XYZ points each, using 1 pair for the support set and 1 for the query set. We find that adaptation to the support set produces high accuracy of 7 out of 9 on the query set. We'll see an example of this in the next 2 slides. To compare the performance to supervised methods, we perform traditional SGD updates using the same hyperparameters as the original PointNet paper on the support set until accuracy converges and we achieve a random baseline of 3 out of 9 on the query set. We then repeat these experiments while keeping the support set constant and constructing 100 query sets. Each query set contains 3 random instances of each ShapeNet class in the support set. Before performing the same procedure as above, we achieve an average of 7.1 out of 9 query set accuracy for our meta learner as seen in the table. In contrast, we see 3.1 out of 9 query set accuracy for our supervised learner. Next, we vary the classes in the query set. For this, we create 100 query sets with randomly selected classes. We then measure the accuracy on the corresponding 100 query sets with matching classes and unique instances. This gives us an average query set accuracy of 7.3 out of 9 for our meta learner and 3.2 out of 9 for our supervised learner as shown in the table. To expand our results, we perform the exact same experiments for 3x5 and 5x3 shot classification with results in the table. As seen, the meta learner outperforms supervised methods for all settings. We note that the 3x3 learner performs with the highest mean accuracy and lowest standard deviation. Across all experiments, there is an obvious pattern that MAML trained on ModelNet 40 is able to classify ShapeNet, a completely different data set with significant accuracy, after being trained on less than 15 samples of the new data. In contrast, the supervised methods cannot be retrained to do any better than a random classifier under the same experiment, showing complete failure to adapt. Here we have the 3x3 support set example with classes hat, bottle, and guitar being learned with 3 examples each. Each picture depicts a point cloud for each instance. We adapt the meta model based on its loss in classifying this 3x3 set. Here is the corresponding query set. After adapting to the support set, we use the adapted parameters to classify this query set. We put a red X indicating the instances with erroneous classification. Across all 200 query sets constructed, we only observe accuracies of 6 out of 9, 7 out of 9, or 8 out of 9, as compared to constantly observing 2 out of 9, 3 out of 9, or in rare cases 4 out of 9 correct for supervised methods. These supervised classification accuracies are no better than a random classifier. In summary, we construct n/k-shot classification tasks from the ModelNet 40 point cloud dataset. We then show that this method performs classification as well as supervised deep learning methods with the added benefit of being able to adapt after a single gradient set. Thank you for your time.